Hi and welcome again to my physics online video lecture series. In today's video, I'm continuing my set of lectures on electric energy and electric potential. Specifically, I'm looking at the second part of this series, which has to do with the various applications of electric potential and really of electrostatics in general. There are quite a variety of applications. The first one that we maybe have most direct experience of observing is that we can use electrostatics to create cleaner air, really not create the air but make it cleaner than what it is, both at home and then in the industrial world. Basically, you can use an ionization filter to purify the air in your home, removing dust particles and bacteria particles and mold spores and so on. And on a larger scale, we use the electrostatic precipitator to clean up the air that comes out of the smokestacks of some industrial plants. A more familiar in the sense that we all actually experience it, though maybe less familiar in the sense that we don't observe it or interact with it every day in a direct manner, is that the synapses of our brain and nerve cells actually use a buildup of electrical potential in order to fire. And so this is kind of similar to building up potential and building up charge on a pair of parallel plate capacitors, really on any capacitor, which is a topic that's actually going to be discussed in the next set of lectures. Besides this, there is maybe a more directly physics as physics application to these electrostatics, which is that we can use the electric potential to measure the electric field or to map out the electric field. And we do this by finding what are called the equipotential surfaces or the equipotential contours of a region of space. And last but not least, we can continue the discussion that we've had in previous lectures of basically what the fields look like near the surface of a conductor by now including electric potential in this discussion. So it's sort of returning to an old discussion from a previous set of lectures and adding to it. So how do we use the electric potential to map the electric field lines? This is actually something that can be done simply in the lab. All you need is basically a voltmeter and then a region of space that you can actually connect the voltmeter to, in which the electric potential varies somehow. Basically, how this works is that you have your electric field lines and you have your line path that you want from point A to point B. So we would measure, for example, the potential difference between A and B, or the voltage drop from A to B or from B to A. Whereas E is negative delta V over delta X. To get the potential, if A to B is sort of a straight line and the E field has a uniform direction and magnitude along that straight line, then this reduces basically to E times L, where L is the length of the path. What the relationship then between the electric field and the drop in potential, or the drop in voltage, is that you can generally create what's called an equipotential surface. That's represented by these green dashed circles in this diagram. And an equipotential surface is a surface around which, or along which, or upon which the potential does not drop if you move from one point to another on the same surface. So this surface right here has a constant voltage of 10 volts. The implication is that if you want to move a charged particle from one point to another point on this surface, you don't actually have to do any work to do that. Or at least you don't have to do any work against the electric field, against the Coulomb's force. You may have to do work against gravity, for example. But since we're talking about electrostatics, it's virtually zero work to move from one point to another on the same equipotential surface. Well, the rule is that the electric field is always perpendicular to the equipotential surface. So in this case, we have a single point charge. The field lines for that point charge radiate outward. The equipotential surfaces are concentric circles that are basically move out from that point charge. In fact, you find that the potential goes like 1 over r, and the E field goes like 1 over r squared. So you can even guess at how close together these concentric circles should be. And again, recall that this is a 2D projection of a 3D reality, meaning this equipotential surface is in fact actually a sphere, assuming that we have a point charge. Or if we're looking downward onto a line charge, in other words, we're looking at a long straight wire from the end of the wire end on, then these surfaces might actually be cylinders. Either way, we represent it as a circle when we project into 2D. There are certain surfaces which, in general, are equipotential surfaces. Basically, the surface in any underlying layer of an ideal conductor at equilibrium is actually an equipotential surface. So if I have a solid steel ball and the steel is acting as a reasonably good conductor, if it's at electrostatic equilibrium, then there is no work required to move a charged particle, say an electron, from the surface of the ball to anywhere inside of the ball. Just below the surface to anywhere inside the ball has the same potential, and therefore the potential difference between any 2 points within that conductor should be zero. You don't necessarily need to have a tangible material object to create an equipotential surface. In fact, there are some equipotential surfaces sketched for several charge configurations in this diagram. And in none of these cases is there actually a physical object present where this equipotential surface is drawn. This is basically a dipole, and so you can see the field lines for the dipole, but you can also see the equipotential surfaces as not exactly concentric rings, but sort of oblong circles in a 2D projection. They're actually oblong pseudospheroids in 3D. Or if these are two wires, they're sort of oblong cylindroids. But there's not actually an object physically present where these circles are. Similarly, if you have a voltage drop between two parallel plates, as in a conductor, then any straight line that is parallel to the two plates in the conductor will itself be an equipotential surface. Now notice this plate is at 100 volts with respect to this plate, means that these lines are going to be dropping in voltage as you move along the E field line. But as long as you move perpendicularly to the E field line, you have a voltage drop of zero. Hence, it's an equipotential surface. The equipotential surfaces are actually very similar and conceptually almost the same as what's called a topographical map. A topographical map is usually used in, for example, a survey. It basically makes a contour map that shows differences in elevation for a given area. So right here we have some map of maybe a campground with some lakes, and you can see that there are different curves that surround the lakes or surround each other. And each of these curves basically represents a same elevation above sea level. So this line right here represents an elevation of 10,400 feet above sea level. So I guess we're looking at some mountains. And as you move in one direction or move in the other direction, you change elevation because you're walking up or down the side of the mountain. So these lines represent a contour at which you are on the same elevation. So if you walk around the mountain on this line, you're not going up or down the side of the mountain. You're staying at the same height above sea level. These curves that are on this topographical map actually represent what might be called gravitational equipotential lines or surfaces, in this case really lines, because everywhere upon the line you're the same height above sea level, which also means you're the same distance roughly from the center of the Earth, and hence you're at the same potential energy, gravitationally speaking. So for a equipotential map in terms of electrostatics, you also end up with a bunch of contours, each one representing a different potential energy with respect to each other. And again, usually when you make a contour map of this sort, you pick a scale, a step size that you care about. So for example, each of these lines might represent a change in height of 50 feet, for example. In that case, this is 10,400, this is 10,450, this is 10,500 feet, and so on. The same thing is true when making an equipotential map for electrostatics, except for that instead of choosing a distance in feet, you might choose a potential value with respect to the ground in volts. So you might have 1 volt, 2 volt, 3 volt, 4 volt, etc., whatever scale you happen to have picked. So let's use this information to discuss the potential on a charged conductor. A charged conductor, you'll recall, has zero electric field anywhere inside of the conductor. So the E field is zero anywhere inside of this conductor, even though it harbors a charge on the surface. That means that there's no net work needed to move a charge from any point within this surface to another point within this surface. That's true if we want to move the charge from the surface to the center, but it's also true if we want to move from one point to another point on the surface of the conductor. So that means that everywhere on the surface of the conductor we have an equipotential surface, and that means that the electric field must be perpendicular everywhere to the surface of the conductor. These two things basically mean, again, no work is required to move a charge anywhere inside the conductor, and it means thus that not only is the very surface of the conductor an equipotential surface, each layer as you move in towards the center is in fact not only also an equipotential surface of itself, but also is at equipotential to the surface of the conductor. What this basically means is that if I was going to draw this as a contour map or as a set of equipotential lines, then I would maybe draw a line here, and then I would need to draw no further lines within it because they're all at the same potential. So I could draw concentric, or whatever you call, lines that are outside of an oblong peanut shape, and those would represent decreasing potential as we move away from the conductor. Once we get to the surface of the conductor, we hit our maximum potential, and then everywhere inside has the same potential. As a simple proof that every layer within the conductor is equipotential with every other layer, we already know that there's no work to move from one surface to another point within the same surface. And we also know that no work is needed to move from one point somewhere inside the surface to some other point somewhere inside inside the conductor to inside the conductor. So the question is, how do we know that inside is at the exact same potential as the surface itself, which is sort of the boundary between inside and outside? And the way that we know is this. We can choose our last surface inside the conductor to become arbitrarily close to the very surface, so that delta x equals 0. And since the work done is basically E times delta x, you have a work done of 0 for an arbitrarily close surface to the conductor, to the conductor's actual surface. So therefore, the electric potential everywhere inside must be equal to the electric potential at the surface, because there's no change from the surface to an arbitrarily small step inside of the surface, and once you're inside the surface, you have the same potential everywhere. So that is one of the physics as physics applications. Now let's look at actual applications in the sense of you use physics to do something that's not just physics. And the first application that I wanted to mention is of what's called air ionization filters. And basically you can buy these for your home or for your office or for your classroom or what have you. And what they do is they purify the air by removing dust particles, mold, pollen, bacteria, whatever pollutants tend to be in the air that you don't want to breathe in that might sort of bother you, give you allergies or make you sick or what have you. And the process is basically looks something like this. Here is air that's represented as having lots of pollutants on it. So the black line is basically air, the blue balls are basically pollutants. So an initial filter is first used and sort of screens out a few of the pollutants. If you go to the store and buy one of these filters, you even have a filter like this, for example, on your air conditioning duct, your intake duct for your air conditioning and heating inside your house or apartment. And what it does is it basically removes a coarse amount of this allergens. Basically, this is represented by the fact that there's a lot fewer of these blue balls than there were initially. In fact, the typical amount that I've seen quoted is about 85% gets removed. That's pretty good, but if you have a count of, let's say, 100,000 particles per cubic meter, then you actually have pretty clean air already. In fact, they make clean rooms that have 100,000 rating. But B, by removing 85%, you're still left with 15,000 particles per cubic meter. And what you really want is to have, say, 1,000 particles per cubic meter, or maybe 100 or 10 or what have you. 10 is pretty dang good. This is clean room in which you're doing silicon manufacturing and you have to put on a bunny suit to walk into the room. Basically, one way of going about doing that is you have a second grid that the air passes through that is positively charged. And as these dust particles pass through the grid, they pick up the positive charge that the grid is basically holding. They basically strip off a few holes, or they sort of lose a few electrons to some of the existing holes in the atoms that are on this grid. So they're positively charged. We place a second grid in which the grid is negatively charged. So that basically ends up stripping out some of these now ionized air particles. They basically bond with the negatively charged molecules that are in the second grid. And so you end up with very few particles that make it through, and then usually there's an additional small hole filter that the air passes through to kind of get rid of a few more particles of air. Then this is going to wherever you're actually sitting, your office, your room, your house, your lab, what have you, and it's nice clean air, fresh air that you breathe. You've removed most of the dust and pollen and junk that's in the air. On a larger scale, we know that if you walk by an industrial plant, you'll often see a smokestack, and you can kind of see smoke coming out of the smokestack. You know that it's dumping various gases, dust, soot, etc. into the air. And this not only maybe contributes to the greenhouse gas count, even if it's not doing that, it will contribute locally to conditions like smog or local air pollution. That's why, for example, if you go to cities like LA or Houston or Chicago even, or New York, the air is kind of dirty in those cities as compared with the countryside. Yeah, you might go to the countryside and smell trees or smell cattle or whatever happens to be nearby. If you're near a feed lot, it's not going to smell nice, but you're not going to have a constant haze in the air. If you go to places like LA or Houston, there's feels like a constant haze just hanging in the air. And a lot of that haze is coming from, for example, exhaust from your car, but a lot more is coming from industrial facilities where there's like a smokestack of some sort. So one way of actually helping to clean up the amount of soot and other pollutants that are in the air that are coming out of this smokestack is to use what's called an electrostatic precipitator. There's a nice diagram of one here. So you bring the dirty air in, and what we have here is a battery. This represents a battery. One side is connected to ground, which is also connected to the basically the side wall of your smokestack. The other side basically is connected to a little wire which winds down. It's going to pick up some negative charge. Your soot and dust particles, dirt particles, whatever it is that you're sticking in the air from the factory, passes through this wire and picks up a bit of a negative charge. And the basic result of that is it's going to end up being sort of attracted to this grounded area that is the walls of the smokestack. And so the result is that most of the dirt sort of falls out towards the bottom, kind of sticks to the side, and eventually you turn it off and it kind of can fall down to the bottom when not in operation. And so this removes up to maybe 90% by mass of the ash and smoke and soot that is being put out by these industrial smokestacks. And then the other thing is that within this ash and soot and smoke, there's often metal oxides that have been created, which are actually maybe valuable to the people who are running this plant. So they're able to recycle those basically. And by recycling this metal oxide, they kind of reap a little more extra profit. And in exchange, you have cleaner air going out of the smokestack. So here is actually a nice side-by-side comparison. Here's a factory that is operating with an electrostatic precipitator, and here's the same factory without. And here you can see a ton of dirt, basically ash, soot, smoke, bellowing out the top of the stack. Here, if you kind of squint right, maybe you can see a little bit, but it's not nearly as bad in this case. So you see the precipitator actually operating here. Another interesting application of this electrostatics is what's called the Van de Graaff generator. And it was actually built We've had these for quite a while now. First one was built in 1931 by Robert J. van de Graaff, hence the name. And of all things, it was suggested by Lord Kelvin. And what happens basically is you have a sphere, a conducting sphere, upon which you're able to place a very large charge, be it positive or negative. And so you're able to produce between that sphere and the ground a potential difference of up to, for a very large, very nicely designed one, 20 million volts between this sphere and the ground. So you can imagine that you'd get some effect like this where you've got air arcing, lightning bolts basically being created by this Van de Graaff generator. And so you could think of it as an artificial lightning generator. In fact, you have seen one of these before in that they make little plasma discharge balls that you can buy that sort of light up and send off little electrical currents from a little ball in the center to a glass dome. And then you touch them and the lightning bolts kind of move towards where your finger is, and so on. So how do these things work? Well, for one thing, by the way, what they're actually used for is, early on they were used as a particle accelerator of sorts. So you'd have, for example, a positively charged conductor, you'd have an ion source, you'd be able to send a few ions through a gap in the conductor, and this very large potential difference between the conductor and the ground basically means that there's field lines moving away from this conductor. You get a little particle that you've shot just barely through. Well, now it's going to be accelerated along the field lines far away to whatever experiment you're doing. The way that this thing actually works, though, is as follows. We have basically a grounded wire here. We have a voltage source which charges a comb, which touches a conveyor belt. And the conveyor belt runs around two different wheels, basically, on either end. And if you look at how this wheel is set up, you can see actually that there's a slight negative charge here on this plate. So that basically causes the positive charge, which is on this comb, to be attracted towards this plate, basically gets stuck on the conveyor belt. And so we move the conveyor belt upward. We have charges on this conveyor belt, and it basically ends up coming in contact with a second comb. And when it gets to the second comb, it basically comes off of the conveyor belt onto the comb. The comb basically picks it up. And because the comb is in contact with the conductor, since all the charges need to be at the surface of the conductor, these charges basically flow from the comb up onto the surface, and we just keep adding more and more charges to the surface, because everywhere on the surface, including the comb itself, should be at an equal potential. And then we have these internal charges on the conveyor belt, which are sort of connecting to the teeth of the comb, and therefore creating a strong electric field that pushes any additional charges to the surface until equilibrium is obtained. So basically, you're able to keep accumulating charges on the surface of this conductor, and by doing so, you are able to charge it indefinitely until you break down the air that's surrounding it. So then you get your ionization breakdown discharge, and that basically produces a lightning bolt that maybe arcs from the surface of the conductor to the ground. So that's basically what the limiting factor ends up being. I wanted to close out today's lecture with a sort of simple example that ties a lot of this stuff from the lecture set in general together. And it's an example that asks, you have a reading lamp in your study, library, office, den, bedroom, whatever. And a typical reading lamp says that it wants a 60-watt bulb or less. And it turns out that the wiring of your house is such that you, if you live in the United States, you have 120 volts from the outlet plug. So your lamp has a potential drop basically of 120 volts, and there's 60 watts of power used electrically. And our question is, how many electrons per second does this need to be in order to accomplish 60 watts at 120 volts? Okay, recall that the charge on an electron is basically Q electron approximately 1.60 times 10 to the minus 19 coulombs. Recall further that power is work done per unit time. So the power here is 60 watts. So this is work per unit time, joules per second. Well, the amount of time we're going to take is 1 second, because it's how many per second. The work done is basically the charge, Q sub E, times the number of electrons that have that charge times the potential difference that they go across, delta V. Delta V in this case is 120 volts. So we can rearrange all of this to say that the number of electrons used, I probably should use a capital N to be consistent with my other notes, the number of electrons used is the power times the time divided by the potential drop times the charge of an electron. So if we plug all that stuff in, we can get a rough value for the number of electrons per unit time. And so the answer actually, this is 60 watts, this is 1 second, this is 120 volts, and this is 1.60 times 10 to the minus 19. 60 over 120 is actually a half. And so this gives us about 3.125 times 10 to the plus 18. So this is how many electrons should be flowing through our light bulb per second. So every second that you're running your light bulb, about 3 times 10 to the 18 electrons are moving through the little filament that causes the bulb to light up. Okay, so that's all I wanted to cover in this discussion of applications of electrostatics. You'll notice that I didn't actually talk much about neurons or synapses firing, and the reason why that is because I'm going to talk about it in the context of having learned about stuff like capacitors and electrical circuit components such as a capacitor, in which you charge one plate and charge the other plate opposite to it until you get a breakdown of the air between the two plates. So I'm sort of reserving discussion of that for a future lecture. So that means that we are done with today's lecture at this point. This is, I suppose, one of the shortest lectures that I have posted for the physics course. And I hope you enjoyed it. It's a little different than what most of my lectures on here have been like. And thanks for watching.